Okay, so good afternoon, everyone. I'm Florian Vandecasteele, and I present you today my research that I'm doing. I'm a PhD student, and now I present the data analysis during and after fire incidents. If you have questions, just feel free to interrupt me. It's a workshop, so I have prepared some slides, I have prepared some things, but if you want to be interactive, if you have some discussions to start with, we can definitely go on. So first, an introduction who I really am and who I'm working for. I'm working at the Ghent University together with IMEC. So we do like software and hardware development. And I'm working in the ID lab. And there we do like all the research that you can imagine related to internet technologies and data itself. So we have people working on machine learning, artificial intelligence, machine learning, big data infrastructures, wireless networks, chip development, and so on. So we have definitely expertise in-house. If you're thinking about new projects, IMEC has also a department in Eindhoven, but we are definitely willing to collaborate. We have a lot of projects. We have more than 500 research projects. We work together with 300 colleagues in our own department. So if you have questions, just feel free to ask us. I'm working more in the machine learning multimedia processing department, and there we have our own group. We call it ourselves Stevia. Why Stevia? It's a spatial temporal metadata extraction enrichment tool to facilitate the context behavior, blah, blah, blah. In such a sense, we do like all data exploration, analysis, and so on. So to give just an example what we could do for you, we have like, for instance, cameras. We try to make as much as possible to interpret what is going on. Where do you need to place the cameras? We analyze the data itself. We analyze the video stream. What can we get out of it? We prepare it so that it's like spatially, temporal, more understanding, that you enrich the data. And in the end, we also do some visualization and human interaction to evaluate what we did before. But it's always like in some kind of loop that we work together. Just to introduce myself, I'm also a firefighter, so I'm working in Belgium as a volunteer firefighter. I'm a background in electronics and ICT, and now, like I said, I'm doing my PhD, mostly focusing on computer vision, machine learning, and that's applied to fire behavior. I think I'm quite unique. I haven't found many colleagues doing the same with the same background, but I'm definitely open to work together with other people, sharing knowledge, and so on. So first, I will show you a short video about smart firefighting. Like we saw this morning, they also talk about data collection, new devices, and so on. A lot of people have an idea how it could be, but it's important to work also on the ideas. It's not like that we can say like Google will offer us a system as a firefighter. No, we should work together and bring the knowledge from Google, from Facebook, and that context with all the sensors, with all the devices that are available, bring it together and bring it to the firefighter.
Yu has a lot on his mind. The challenge of being a first responder can be difficult to manage. Sometimes it's easy to daydream about the future of smart firefighting and how it will make the day-to-day burdens easier to handle. You can imagine rushing to save victims while wearing an exoskeleton with built-in sensors and face shield that incorporates augmented reality. He's able to stream real-time video to see his team's current positions and gain valuable updates. From there, a next-generation fire truck incorporates drone data, pulls up real-time images of the site, locates smart sensors on the premise, and locates the fire to identify where victims may be inside. Oh, and it's driverless. You won't have to dream about these amazing innovations for long. The We Respond community is dedicated to exploring cutting-edge technology that will advance the future of smart firefighting and help you respond faster, smarter, and safer.
So, as you can see, there's going a lot on. Also, the community We Respond has some ideas. People worked on that. But I think it's also a matter of bringing the knowledge together and think, what do we exactly need? So, to just bring in the context and the problem itself, if a firefighter arrives at the scene, what he mostly does is like doing a 360 route around the building, looking what is going on. He tries to get as fast as possible, as much as data as possible. But he has definitely some questions. the structure of the building, the position of his firefighters who go inside, which is the layout of the building, for instance. Where is the fire? What are the dimensions? What is in the building? Are there still people in there? What is the fire severity? How is the fire propagating? And so on. I think now when we arrive at the scene, we can get such an idea, but it's rather small. We can use more and more data that is available. So if we look to the existing tools, me as a firefighter in Belgium, what we mostly have is like, we have a sheet just on paper, mostly. Maybe we have a rugged tablet with such a device, and that shows just like the geographical information, some GPS, some preliminary steps, like those are like the fire resistance walls and so on. But there is no real feedback. We don't see the CCTV cameras. We don't see the smoke alarms. We don't have that kind of data. I know some people worked on that before. I also see some colleagues here. So it's just a matter. But if we look what's available, firefighters, mostly in Belgium especially, we go inside with thermal imaging devices. But there is no feedback. The officer on the scene, he does not receive the data that's available in there. We interpret it ourselves. Every firefighter just look with the thermal imaging device and he interprets the data itself. He looks to the video stream, and with his knowledge, he made decisions. Maybe we can work together and make decisions based on what's available. We have like, the bodyguard who is protecting ourselves. So if we collapse, there's some kind of alarm. You can also connect that. So bring it outside to the fire officer. There are also people working on that just to see like the oxygen level consumption and so on. I like mostly what we also see in buildings. We have a screen, just a simple screen with some LEDs, and those are showing, in this region there is a fire, but that's it. We can do more, I think. So if you look into that, we have like already some solutions available. Drones are popping up everywhere. There are also research going on, especially in the firefighting field. We have smart homes, we have Internet of Things. Everything gets connected. More and more data is available. Also see-through, some augmented reality, virtual reality. There are definitely things going on. But for the firefighting community, I think we need to bring it together. Firefighting is always like interdisciplinary, so we should work together. So before we did the research, we also asked real firefighters and other colleagues, what do you need? What do you expect? What do you allow? So we launched the questionnaire. It was just in Belgium. I know maybe it's a bit biased, but it's just like we asked, what do you want? I know it's biased also in the way that the people or the firefighters just answered by what they knew. Maybe they weren't aware of new systems. They weren't aware of what could be like within 20 years. But what was, for me, a bit promising, like 96% said like we want to have a thermal imaging device. Also, they want to have, 65% wanted to have visual information of the scene. They wanted to have CCTV cameras, what is going on the scene, and so on. Also like the time allowance, so we asked like, if you have a device like drone, how many time do you allow before it's set up? And in an average, it's in something between 0 to 5 minutes. Most of it allowed it when they arrive on the scene. So it should be fast. It should be quite easily to set up. But I think with the thermal imaging, they are quite used to use it. So it's just bringing and interpreting the data. As we look into literature, there's definitely some work also like from NetEdge. So smart data, smart connections, there are things going on. Also the roadmap of NIST, they launched it and they said like smart firefighting, what do we want? How do we see it in the future? But unfortunately for me, lucky for me on the other hand, I haven't seen so many people working on it. So if some people has like more funding or definitely interest in working together, I think smart firefighting should be more like popping up from the firefighters itself. Together with research, together with fire safety science, we should work together and bring it up. It's not just a matter of ideas, it's combining everything that we have. Also related to that, we have like smartphone apps. So smartphones, people use them everywhere. Sometimes firefighters wear them. Sometimes it's not allowed. Mostly it's not allowed to wear it when you are on duty. But with the smartphone, you can collect a lot of data. You can know where people are, for instance, where your firefighters are, on the other hand. What are they doing? So Kunu Fire launched they made a system, and they know by the sensing devices that are available in the smartphone what the firefighter was doing. So they know if he was running, if he was walking, if he was stressed, or so on. So there's a lot of data, just bringing it together. On the other hand, when we look to firefighting, there are other things that like basic firefighters learned in the beginning. So for instance, this is like from CFBT, they have like different correlations. What as a firefighter do you need to look at? Like this morning, they showed us like the basic version and brought it together to like just a triangle again, to the fire triangle. But the data that is in there is very important. Like for instance, just like here, like you see, smoke. Smoke has a lot of information. It's like the color, the flow, what is going on, the thickness, the volume, and so on. So if we combine it with the sensing devices and the frameworks that are already available, I think it's a rich source that we can get something out of it. And it's also good because like firefighters, some people are stuck in their thing that they know. And I think if we combine it with things that they know, it will be more easier to understand. So based on that, some background, I made my own system, I wouldn't call it. It's like a combination of bringing blocks together. We have like building information models. More and more buildings are made with software. Automatically, it's annotated. You know a lot about the building. You know which doors are in there, what are the properties, what are the fire properties, what are the sensors in there. So it's a rich source. On the other hand, we have like the BSSAHF in a Dutch GeoRes-TV model. It stands for Building, Surrounding, Smoke, Air, Heat, Flames. So if you have all that kind of information, you know everything about your fire. So if a fire officer or like a firefighter goes to duty, and if he knows a lot of information about each block, you know a lot what is going on. On the other hand, we have the handheld sensing, the active sensing, more and more sensor, so I worked on that. And then in the end, we do some fire behavior analysis. So futuristic, I think it should be like a commander gets some information from the incident. He sends some information to the incident. The building model is also updated because like when a building was built, maybe it was like 10 years, 20 years before the fire happened. Maybe they changed the door, they changed the wall. I think when the plan was made and when the fire occurs, there's always something different. So if you ever want to make a system that is able to do some fire forecasting, for instance, we need to have an update of the building itself. And with that combination, you can do different things. You can do fire forecasting, evacuation guiding, and so on. I know fire forecasting is currently not possible. In real time, it's not possible. But maybe within 10, 20 years, we can go to that. But what they are lacking is real-time information from the scene. They need to have information from what is really going on and where we want to make predictions. Like for a firefighter, I think from my point of view, it's interesting to know, for instance, the heat release rate, to know when flashover will occur, when there is a dangerous situation. Maybe within the future, we can forecast the fire gas ignition and so on. So you need some information from the building, from the real-time scene, and then it will be possible, I think. It shouldn't be like a detailed CFD calculation with like the temperature drops from 1.0 Celsius or whatever. I think it's mostly interesting to have like another kind of thing, just like with simple warnings, for instance. So now I will discuss a bit all the blocks that I talked about. And it's research that I did in collaboration with other people. And due to my background, I work mostly on a computer vision data analysis. I will show how I did that thing. So as I already mentioned, the building information modeling. So for people who are not aware of what this exactly is, it's a system. It's mostly software. It's annotated with a lot of things that could be done. Mostly it starts with like the building. Architects have an ID. They draw their own ID, but they do not concern about stability, about fire safety. They are not interested in that. They just want to have a nice building. That's what they want. And the structure and all the rest, it will follow. But like with building information, you link everything together. You link it until the fabrication, until the construction, and also in the end for the maintenance and the renovation. It's a data set. I wouldn't say it's a data set, but this is like all the objects, all the elements are in there. They are annotated. They have their own properties. They have correlations, so we have some links. So for instance, a room will have some walls, will have some doors. The walls will also have some properties. So everything is connected to each other. So it's a rich source. So if we look into firefighting or fire forecasting, fire safety, what can it offer? For instance, automated rule checking. A lot of companies have some rules, have some legislations that says, like, for instance, you need so many fire-resistant doors. You need a maximum of 30 meters before you reach door. Those are like simple rules that you can check in the building. So you don't need any more an architect or people looking into that. Evacuation planning, maybe it can be automated. There are people working on that. Sprinkler setup, like smoke evacuation systems. Where do we need to place them? That could be all done in building information modeling. Also for the fire forecasting, you can extract the data and put it into that. And maybe also the data visualization. Maybe within 10, 20 years, we will see such a scene when we arrive as a firefighter. We will see like, there's the alarm, there's that going on, there's so much smoke there are still people there on that scene. And maybe that can also be visualized in the building information model. So as I said, the building information model has a lot of data, but also a lot of problems. Maybe the building was outdated. So we need an active system that updates what's going on inside. And that brings me to the handheld sensing. So that was at the real fire in our city, like how firefighters mostly hold the thermal imaging device. So if I would ask you what is going on, where are they? Where are they in the building? What is burning? I think it will be a hard question for you. So I'll let you watch some more. So if someone knows what's going on, please pop up. So actually, it's a fire in the basement, and the refrigerator is burning on the right side. So if you want to do some data analysis and video analysis and automate that, I think we need data analysis, computer science, but also some guidance for the firefighters itself, how they need to wear the thermal imaging device. So it should be like a bit from both worlds. But as you can see, it will be difficult also for computer vision. So for me, there was like the video. I'm quite an expert in doing video image analysis. So as I started with the inputs and I tried to detect the objects, detect where is the refrigerator, where is the bookshelf, where is the bed or whatever. Where are we? Are we in the basement, the cellar? Are we in the living room, for instance? Because like when you know I'm in a living room, you know more what could be in there, what could be go wrong. If you know I'm in the bedroom, you can assume, or most probably there will be still people in there, or you can make your own assumptions. We can see where is the smoke and where is the fire, and maybe in the future we have like this image, and out of the image the answer comes like the fridge is burning, and so on. So I tried to make such a system. I know it's a bit hard. And the first thing that I did was like object localization. So what I did, I went to the IKEA in I want to make a, a statement, but just like it was easy for me to collect data because like I haven't seen data with like all rooms configurations in the thermal fields and in the visual field. So for me, the only solution was to go to the IKEA and to shot some movies with the visual and the thermal annotated images. And there, what we did, we collected the data, and object localization consists of object detection and classification. So first you want to know where are there some objects and which object it is. And then we did some transfer learning. So transfer learning is a technique used in machine learning. And what they do, they have a large data set. So for instance, Google has trained the system with thousands, millions of images, but we only have 1,000 images from the IKEA. And we want to transfer the IDs that Google has to the data set that we had from IKEA. That's basically what we are doing. And we train the system with transfer learning, and we succeed, actually. So actually, in the end, what we got out of it, we have the visual image, we have the thermal image, and we were able to recognize objects in there. We recognized here that this was a couch. We recognized that this was a closet. For you as a human, it is not possible. But as you can see, a computer is able to detect objects, to know where you are, to understand what is going on. I know it's a bit biased. It's not in fire environments, but to collect data in real fire environments, it's even harder than just collecting just simple rooms. I know that, but if someone has some data or has some ideas to shoot movies, I'm definitely willing to join. So in the end, we got some objects. Here it is in the visual spectrum, but as you can see before, it was also in the thermal spectrum. When you have objects, you can also make some assumptions. Because like, you know your fire load, for instance. If you know, I have a couch, I have a closet, I have a bed, you can make an assumption. You have, yeah, I know it's a bit, yeah, sometimes it depends also on the growth or the oxygen. We saw it this morning. But to make a simple assumption, it's better than just standing outside and knowing nothing, actually. When you stand outside, you know, okay, it's a house. How is it filled? When a fire occurs, mostly it's happening when something changed. When there is a party, for instance, or when people just replaced everything. It's not always just as simple as that. So heat release rate, why is necessary for us as a firefighter? You can use it to do some basic fire forecasting. You can use it to predict flashover, for instance. You know a bit about the fire severity. So with the objects, with the room configuration, with some tests that they've done in the future. So there were a lot of tests in history with they just burned couches, tables, closets. I think it was a fun time. They went to work and what they did was just burning objects. So they got a lot of data out of it, and by combining it with the new real objects, I think it's very interesting. Also the room configuration. So out of it, for you as a human, maybe it looks simple to understand, like where are the walls, where are the roofs, where are the connections between. But for a computer, we train the system, and here the blue lines are where are the connections between the wall and the roof. It's also easier to understand, like when you would be in a smoky environment, to have like the outline of your building. Also to give feedback to the building information. Or the walls changed. Is the door still in place that we initially placed it on the screen? And so on. There's also some other work that's been done on feature learning, feature engineering. And there they used it to know where is the smoke, where is the fire. So maybe within 10, 20 years, there will be robots, but they still need to go to the fire. From my assumption, I don't think robots will be able to do the complete fire job because like it's always different. It's always something else. You have a lot of things that you need to consider. So from my point of view, I think robots can be helping us, but I don't think robots will completely take over our fire duty. So in the end, when we combine it all together, we try to make a system starting from the image to get the answer out of it. I know it's like we still made some assumptions, and We still need to do a lot of work to make it a real system, but I think I show it is possible to start from an image, to extract the objects, and to get a better understanding from what is going on. I think if a fire officer would get this information, like when he arrived, I think it should be like quite easy what his tactics will be, what the risks that he wants to take, and so on. As I said in the beginning, it's also a way of working together with the firefighters, give them some advice. And here I listed some advice to use a thermal imaging device. Because like when you give it to a firefighter, he will hold it like we saw. But like it's just use it straight, use it slowly to get a complete overview. Avoid the presence of persons. Like if a person is standing in front of your camera, I know it sounds a bit logic, but people are quite often pointing to persons and they don't see what they see. Also on a reflective surface, you have, maybe you saw it before, but you have funny movies about firefighters trying to put out the fire, but actually they are trying to put out the fire in the mirror, because like you have reflective scenes. Like a thermal imaging device can't see through reflective mirrors. So it looks, or it sounds a bit strange for some people, but it happens quite a lot. Also, yeah, you can use it to see the fire conditions and so on, but also like we saw this morning, it can't see through furniture, it can't see through debris, so you can't see through the floor. Be aware of that. A lot of firefighters just use it as a simple tool, use it not the way it could work, I think. So it will be a bit from both worlds. Maybe the thermal imaging device will be smarter, give some annotations, give some feedback, but also the firefighters itself need to adapt them. So back to the active sensing and the low-cost sensing. For my master thesis, I did some work and I created the fire gas system. So there are a lot of real fire experiments. And what they do is they put things on fire in tunnels and domestic homes and so on, but they need some more objective manner to evaluate what was going on. So we created the system which can integrate the sensor, the streams, the mapping systems. We do some analysis, so spatially, temporal, what is going on, and we can make some visualizations. So for the smoke itself, it starts always with the camera position, where it's pointing at how is the video stream, is there like some real-time link. We can estimate the visibility, like for firefighting or evacuation, visibility is a major factor. We can do the mapping, that could be done in different ways, and we can do some analysis. But I will go to this slide immediately. We also created the system, so in the tunnel between Brussels and Antwerp, we had some real fire experiments, and they wanted to know, like when they used the smoke extraction system in different ways, what was going on. They had a lot of cameras. There were like 20 cameras hanging around. We got all the data. Unfortunately, for every camera, it was like 1-2 gigabyte. It was like 1 hour shot. And we run the test like 6 times. So we got a lot of data, and it's like big data, blah, blah, blah. But in the end, no one was interested because like there was an explosion of data. So what we made was like a simple algorithm who was analyzing the video stream itself and just shows where the visibility was okay or where there were some changes, and then you can look to the screen what was going on. We created our own algorithms and they used the information, but I won't go in detail for that. Another test that we participated and who had quite the same problems, it's also presented here. So Peter Poppe, colleague of mine, worked in the VIPA study, and there they had 5 fire experiments, and they wanted to know in elderly homes what was going on, because like you have more and more common spaces, they are in the evacuation route and so on, and they wanted to know if a sprinkler system, a smoke evacuation system could help, like placing fire-resistant doors and so on. And they monitored it. That was the scene that we have, and they monitored it with visual cameras, thermocouple trees, a lot of sensors, a lot of data, but the same problem. too much data and no one was interested. So what we created was like heating maps. It was like for them quite intuitively, and they had a slider where it can go over time. And with that system, though, the red dots are like no visibility, and the more blue it is, the better the visibility it was. So we created such a system for them. It was just based on the video streams, and in the end, it was more easier for them to understand what was going on. Otherwise, they wouldn't be interested in the video data, although it was available. Also for the smoke, we can generate some other graphs. We can get out the smoke height, the smoke visibility, and some other parameters. So we created that system for them. It's like very intuitive what was going on. So in the end, we created the system for them. We have the video streams, we have the data analysis, we have the thermocouple trees. So I also want to show this to you because like data visualization is something important. You have your data collection. As we said before, you can do some analysis, but the way that you visualize your data can change a lot. It's not always by looking into new figures or new things, but like visualization your data in another way could help you to better understand what is going on. So back to some other properties. The flame dimensions itself, so when you have some tests, you sometimes want to know what is the flame height. Also for heat release rate, we have the objects. Objects can give some information what is going on, which object is burning, but in combination with the flame height, we can give a better estimation about the heat release rate. So when we look into literature, we have different formulas to calculate it, but how are they evaluated? No one could really answer that question for me. So what we did, we created some slices, and when you have real fire experiments, we can create such graphs, and we can create like the flame height. And we have our own system who was able to give like the estimations. I know it's a bit shifted to that, but that can be to the lighting of the camera. So if you have a real fire experiment, we can give you the software to evaluate the flame height, the flame dimensions, and so on. Another movie that was asked to calculate the flame height. And as you can see, we also have the linear flame growth and so on. So we have like different properties, fire properties. We had the smoke, we have the objects who are burning, we can estimate the flame height and so on. So we are working on different parameters itself. Also for a tray, so cable trays, they placed some cables in there, and they wanted to know what is the flame propagation. If we add some material, what is going on? And for them, we also created such a system who was able to show some simple plots. Like I said, like with simple visualizations, you can get more out of your data. So in the end, we got like the building information modeling. We will give, that's part of my future work. We give a lot of information. We have the handheld sensors. We can do some active sensing. But in the end, we want to have some fire behavior analysis. I'm also working together in the PRETREF project. So that's with the fire dynamics and combustion group of Bart Merci. He is known in Ghent University and I think also here in the community. And they do a lot of work on forecasting, on CFD calculations, combustion understanding, and so on. So they asked us to give more data about the fire scene and bring it to them. As a last part, as I said, data visualization is also something important. And in the same questionnaire that we launched to get an idea about the information that they wanted, the firefighters, we also created some mock-ups and asked to the firefighters, like, how do you want to see your data? If you ever have data, how do you want to visualize it? And we asked them, and we got different feedbacks, and they liked to have an overview with like simple things, video streams, but with also like simple bullets from your safety level is not safe anymore. your oxygen is low, your temperatures are too high, or so on. And I also think augmented reality and virtual reality, we know working on a project that will be able to integrate the data in your screen. So firefighters have their own screen, and we want to project the information right on that screen. And to try to not be obtrusive because you can place a lot of cameras and a lot of things, but as a firefighter, you need your own view. Still for safeness, for safety reasons, you need definitely your own view. So as a part of future work, recently, if you ever come to Ghent, please also visit the new home lab. So our lab built a new house, and it's equipped with all the latest Internet of Things sensors. You can measure almost everything. So if you ever have a research question to that, we have the house. You can have your own experiments as you want. You can't put fire in there. That's the only thing they said to me. You are not allowed. So, but still, for a lot of tests, it's definitely great work, I think. And also like smart dashboards, smart visualizations. There is a lot of work going on, and people thought about it, like we saw in the movie. A lot of people thought about ideas, but I think it's now the time, to bring it, especially to the firefighters, to bring the ideas together, to make the systems able. I think, as I showed with machine learning, we can do already quite a lot. It's just bringing the right people, the right devices, the right software together. So in the future, I also want to validate that. So if you have real fire experiments or you are aware of, please contact me. I'm definitely willing to go all over the world if it's necessary. Improve the calculations of the visibility, the smoke height, dimensions. I'm also working on the sensor data, combining it with building information. Currently, I'm not able or allowed to show it today here. And the handheld sensing, the thermal imaging device, it's a rich source. It's already used for the firefighter, so they know almost to handle it. And if you bring that data to the officer, I think it's great work. So some conclusions. I hope this can be also a starting point to make the firefighting more sensing, data-driven. They have a lot of questions when a firefighter arrives. They want to know quite a lot, and I think with data, with sensing, with machine learning, we can bring it together. And for me, that's a bit my end of what I wanted to talk to. But if you have questions, recommendations, something else that you want to say, feel free to interrupt now. We still have some time.
I have a question about privacy. We're doing quite some research. I'm from Delft University, and we do quite some research on sensor data collection and BIM. And we're often challenged by this privacy difficulty because we're gathering information from people, from individuals, and it's not allowed at this moment at least. And did you ever go with that, or did you have this trouble as well?
Yeah, for every experiment not related to that, we always have privacy issues, but I think it's just a matter of awareness of people. People are sharing everything, actually. We got I'm not allowed to say that maybe here, but we got data from different sources, from different companies. They offer us quite a lot. They know where we are, what we are doing. If you ever use an app to go for running, all the data is in there. Your heart rate, your position, everything, every second is monitored. And why are we still concerning about privacy? I know it's a big issue. I definitely want to bother it, but I don't think maybe within 10 years everyone accepts. When you look to China now, they have their own system now based on some points that they give for people if they are doing well or not. And the system is just based on cameras and Internet of Things devices, and everyone accepts that system. So maybe we are still in a shift phase.
I guess so.
Yeah, I think there is definitely data and things available that can help, but we will see where it ends.
You were talking about low-cost sensing. Is it only the cameras, or did you also use physical sensors like temperature, pressure?
For the real fire experiments, we want to use that kind of system. So for the fire experiments that we that we monitored, they were like thermocouple trees. Those were like the industrial large ones, but like just a simple smartphone. I think not many people are aware what kind of sensors are in there. We have like pressure, temperature, gyroscope, GPS. There are definitely a lot of sensors in there. So I think a smartphone is low cost because like everyone has it already. So why wouldn't we use it?
This morning we saw cameras can see through objects. You said you have 20 cameras inside of the tunnel. In your machine learning algorithms, your image recognition, do you have trouble finding out what the height is?
Smoke height or?
Smoke height or fire height? When there's difference in distance from that layer. So
and that's a bit the problem. When you look to CCTV cameras, they are placed always on the ceiling. But yeah, that's a problem, and you can't see. But like, for instance, if there is a room and that's burning, and you look through this camera, you are able to see what is going on. And we use also the combination of sensors. Maybe that wasn't quite clear here in the slides, but we use the combination of sensors. If a sensor fails, for instance, like in the tunnel experiments, there is always a check between the sensors. So one sensor can't say like I'm 1 meter and the sensor in the neighborhood says like 2 meters, for instance. That's not possible. Then we say like this sensor is failing, but that's done automatically. But we are still aware that if the room is filled with smoke and the camera hangs on the ceiling, then we will have a problem. But initially, to see the fire growth, to see what was going on, which were the objects in there, you can do it still with normal cameras. And there we have also the thermal imaging, which is worn by the firefighters who go inside, so it should be some kind of feedback if some data is lacking or not. But yeah, that's definitely a problem. 2 more questions, remarks? You have? Nope. Okay, then I think you are free.